lectures. So please, Nima.
Okie dokie.
An evening lecture. Are you prepared?
So lucky you guys, I have a flight to catch tonight, so you won't be here.
At 11 p.m., so...
Yeah. No, in other summer schools, my favorite thing to do at schools is to actually have night sessions where we talk about our secret worries and hopes and dreams and so on. So maybe some other time we can have a hopes and dreams session. Or we could have it now if you wanted. All right. Okay, so, all right, so I want to just finish saying some things about the Feynman-Fan generalities. So remember, we got this picture where if we just look at all the vectors, all the g vectors, they uniformly cover the entire space. They're made out of cones. The cones correspond to Feynman diagrams, and they cover all of space together. We just, at the end, talked about the fact that in general it's infinite. There are these little lower dimensional missing pieces that are actually associated with uncolored particles. Okay, so, but putting that aside, the fact that already we saw, in our simple example, the fact that all the cones snugly fit together actually implies projective invariance that we saw yesterday. Okay? And I will leave this actually as an exercise for you to prove. But I'll tell you the answer, so it's easier to prove when you know the answer. So remember, each one of these things is associated with a variable now. Well, we're calling it 1, 3, but let's go back to labeling them like we were yesterday, x13, x14, x24, x25, x35, and so on. And remember that yesterday we noticed that if we wrote the form as d log x3, d log x14, plus the cyclic with all the plus signs, that was important, that this form was projectively invariant. And remember, what was the sort of content of this? Is that when we checked under d log of any x shifts to d log of x plus d log alpha, we wanted the coefficient of all the d log alphas to be 0, right? But what happens when I do this shift is if I, in general, have some d log of some x1 through d log xn, I'm going to get out of this things that look like d log plus or minus. I can pull out the d log alpha in front of the whole thing, and some d log x1 of d log xn, where some guy in the middle, d log xi, I leave out, right, in the usual notation, right? So the fact that it's possible to choose the signs for all of these things to cancel is telling you something about the fact that, if I have n things coming together, if I have n minus 1 of them coming together, the way the n minus 1 come together is it can cancel between two different diagrams. All right? Now, that's exactly what the fan is telling us. Because in the fan, and we see this in the two-dimensional picture, but it's a little more interesting in higher dimensions. Here's a cone. That's one diagram, right? There's a nearby cone with a different diagram. So let's say it was a three-dimensional picture. Then I'd have, 3 vectors here. This is one cone. That would be one diagram. Here I'm drawing the sort of cone. There would be another cone here, which is another diagram. Right? As I go from one cone to another, I'm just changing one of the rays. Okay? 2 of the rays are in common. There's one ray on one side. I'm removing and adding it on the other side. So that means that they're agreeing on n minus 1 of the rays. And all I'm doing is flipping one to the other. So that gives a chance for the signs to work out. Right? Because that means when I look at all of the d logs together, then if I look at the coefficient of any given d log alpha, the n-1 guys that occur there will come from exactly two cones. Okay? The one with the variable that I took out on one side and the variable that I took out on the other side. So the fact that all the cones fit together means that there's a chance for all these variations to cancel. If they didn't fit together, it would be impossible, because that would mean that there would be one cone here with no friend on the other side. Okay? Or if there was a hole in the space, then its friend might be over there, but they wouldn't actually snugly touch each other. The fact that they all snugly touch each other means that there's a chance for the signs to work out so that the variation is projective. And I will leave it for you to prove the following, that I can actually, in our examples, remember, we tried to find the signs, we determined a bunch of them, and then we found the rest of them just had to work out. So this picture actually tells you what the signs are ahead of time. So I'm going to tell you what the signs are. Now you can prove with this choice of signs that the form is projectively invariant. So here's what you do. The form is equal to the sum over all the cones, which are all the triangulations, all the Feynman diagrams, d log of, let me call it xi1 through d log of xin, whatever the n is, right? Whatever the dimensionality of the space is. But what I have to multiply this by is the sign of the determinant of the g vectors for I1, gxi1 through gxin. That's the sign that you need to assign for every cone. All right? Okay, so for any given cone, and you see it's very nice because you might think there's some arbitrariness in how you write this form. After all, the d log, d log, d logs are antisymmetric. So depending on how you present them, there might be a sign in front of it. But the determinants have exactly the same sign. Okay, so no matter how you choose to write out the x's, you write the g's in the same order, and the sign of the whole thing is unambiguous, right? Okay, so this tells you exactly how to choose the signs for everybody. And the claim is that this form is projectively invariant. Okay? So this is one of the things that again, yesterday we understood this from a dual point of view, that the projective invariance meant that the canonical form, when you pull back to the subspace, should not have any singularities at infinity. This is now understanding it directly from the fan, and it has and we can also be more specific about what the actual sign is. Okay? There is a second remarkable fact, which is related to why we should sum all of these diagrams with the same weight. Okay? So that was the other. This is something else that I will just state. It's actually quite easy to prove, but I'll just state it, and you can see that it's true here. Here's a nice observation. If you look, so we looked at the sign of that determinant, but in fact, if we look at the determinant of these g vectors for any cone, gxi1 through gxin. So this is a measure of the sort of volume of the cone. Of course, the actual cone there's some infinite cone, there's an infinite ray, they're bounded by infinite rays, but the g vectors are some nice God-given things, so it's also reasonable to just look at the volume of the little cone that's literally bounded, its vertices are literally bounded by the tips of the g vectors, okay? That's what that determinant is up to sign. And the beautiful thing is that this is always plus or minus 1 for all cones. Okay? So in a very specific sense, all the cones are as big as each other. Okay? This also means that if you take that form that we defined on kinematic space, remember, the third thing we talked about, the second thing we talked about yesterday, is that we can pull back the form to a subspace, and on that subspace we get the amplitude, right? All the minus signs go away, we just get the amplitude. Well, we can also see that here, and we can also be very specific about what that form is. So I have all these x variables, all these xi's, all these capital X's, but I had 5 x's here, but I have a 2-dimensional space. Okay? So in order to find a subspace, I have to parameterize all of the x's in terms of some 2-dimensional space. Right? So in general, the parameterization is that if you have a curve x, I'm going to write the x for the curve. I'm going to parameterize all of them in terms of a lower dimensional space, precisely given by the g vector of the curve. So I'm going to write x sub c is equal to the g vector for c dot some little x. This little x is just some auxiliary variable that labels where I am on this plane, okay? But its dimensionality is the same as the dimensionality in which the g vectors live, plus any old offset, dc, just a constant, okay? This defines some plane in the big space of the kinematic variables. And exactly because of this wonderful fact of the determinants and that formula for omega, you can show that omega restricted to this plane, to the plane where xc equals g dot x plus d, is exactly equal to dn of this little x multiplied by just the sum over all the diagrams, the product of 1 over x for all the diagrams, which is the amplitude or the integrand for the amplitude. Okay? So that's the other phenomenon that we saw yesterday. Okay? So we have, I remind you, last time we just write down all the curves. We give them, we figure out how to label them by our left-right paths. Words. We just build the geometric vectors. We project through the boundaries, and then it just happens. We don't do anything. It just happens. The space gets divided up into regions. The regions correspond to Feynman diagrams. They all have the same volume, okay? And that fact, they all snugly tile together, and that tells us that if I build the sort of most obvious form that I could, if I want to build. You see, why would I write this thing down? I want to write d log xi1 to xi, and oh, look, shoot, too bad, I can't do it. What does it even mean? They're ordered in some way. You know, what does it even mean? What signs to put? Oh, no, but I can, because there are these naturally the vectors that are associated with it, okay? So you even do this. This is the only thing that you could write down that would even make any sense, all right? And this object now, because of the tiling property, is projectively invariant, and there's a subspace on which all the signs disappear, and I get what you would think of as the amplitude, okay? All right. So now we're going to switch gears. Yeah. Yes. That's right. No, this is the same thing. This is the same thing. This is the same thing. Yeah, it's a slightly different way of expressing it. So yesterday, we wrote down the equation where we solved for all the x's in terms of x13 and x14 and plus some c's, okay? Today, I'm writing everything down. So yeah, you're right. It looks slightly different, but it's actually essentially the same. Yeah. Yes, that's right. But it's very close because for those x's, for those curves that are the basis vectors, their g vectors are the basis vectors. Okay, so that's why if you write x equals g dot little x plus d, then the capital X and little x's are basically the same thing. Okay, so for those curves that happen to be in the triangulation, the g vectors are the 1, 0, 0, 0, 1, 0 are the basis guys. Okay, that's actually a very nice thing that you can prove from the peak-valley formula, okay? That you can prove that if you look at any curve in the inside of your triangulation, the word that goes along with it, there's a word where you exit in both directions and you turn left forever, and that word is one which will go down and will uniquely hit your curve, your road in the middle, and will go back up again. And so that's a way to build the word that goes along, the curve that goes along with that. With the g vector in that direction. So this is why you can sort of go back, and there are always curves. The arcs that correspond to the roads that you see in the triangulation are always associated with words that look like a V. Okay, and so those are always things whose g vectors are going to look like basis vectors. Okay, that's part of something that you'll discover if you actually do the linear algebra exercise I was suggesting to actually do the projection through the geometric vectors. So if you do that, you'll sort of discover all these things. Okay, so now we're going to switch gears. But this fact that all the cones fit together and tile the space gives us inspiration to do something. So the fan, which means that all diagrams, fit together, we're going to use this as an inspiration to find what we'll call a global Schwinger parametization. Which is going to give us an expression for amplitudes. And this is going to be integrated amplitudes as an integral over a single integral over a single space. All right. You'll see what I mean by this in a moment. So let's go back and remind ourselves about ordinary Schwinger parameterization. So just so I don't, I'm going to imagine I'm doing all these things with like Euclidean momenta here. So 1 over p squared plus m squared. That's just so I don't write i's. All right. So just nothing. You could put everything here, Loren, any signature you want. It doesn't matter. But I'm going to write it this way just to make it easier for me. This is integral 0 to infinity d alpha e to the minus alpha p squared plus m squared. Right. So this is what you all know as Schwinger parameterization. If we're calling this 1 over x, so this is what we're calling 1 over x instead, well, then Schwinger parameterization is 1 over x is integral 0 to infinity d alpha e to the minus alpha x. Okay? And so we normally don't talk about doing Schwinger parameterization at tree level, but we could, right? Let's do tree level, loop level. Normally we talk about a loop level because it makes it easier to do the loop integrals, but let's just even think about it already at tree level. So, if I have this diagram, let's say, then I could write this as, first let's just even do a totally old-fashioned language. I have some Schwinger parameter d alpha 1, e to the minus alpha 1 times, p1 plus p2 squared plus m squared, and then e to the d alpha 2, integral d alpha 2, e to the minus alpha 2, p1 plus p2 plus p3 squared plus m squared. Right? I won't keep writing 0 to infinity. I might forget sometimes. So that means that, or we could write it I'm just doing the same, I'm not doing anything, it's just cosmetic, I'm just writing it. If I draw this picture, I could say this is, in Schwinger parameterization, integral d alpha 1, d alpha 2, e to the minus alpha 1, x1, plus alpha 2, x2. Okay? Or alpha 1, x13 plus alpha 2. So, in fact, let me call this d alpha d beta, just to stress d alpha d beta, e to the minus alpha x13 plus beta x24. So we can think of this as an integral over this upper quadrant in alpha beta space, right? So I'm integrating over alpha beta space, e to the minus some function of alpha and beta, e to the minus alpha x13 plus beta x24, right? Now, already here, you can have kind of a dumb idea, okay? I said, oh, this is great. I'm now going to express the entire amplitude as a single integral over, an integral over just that upper quadrant, alpha and beta, okay? So the amplitude is like 1 over x13, x24, x14, plus 1 over x24, x25, plus dot dot. So, brilliant me, I'm going to write it as e to the minus 0 to infinity d alpha d beta. Look, it's just one integral of the same space, alpha and beta, of what? E to the minus alpha x13 plus beta x, sorry, this was 1,4, plus e to the minus alpha x24 plus beta x25 plus dot dot. Okay? Why aren't we impressed by this? Okay, we're not impressed because it's utterly empty of content, right? I just took the 5 diagrams, I Schwinger parameterized each diagram, and I shoved them together under one integral sum, right? What, apart from the fact that it looks stupid, there's another problem with it, which is that there's no way to line up what I mean by alpha and beta in one diagram compared to what I mean by alpha and beta in the other diagram, okay? Okay? I could have just as well called it beta x24 plus alpha x25 in the second term and just randomly changed what I mean by alpha and beta. So it is cool that one diagram is somehow associated with this region, right? But there's no meaning about, there's no sense in which these regions can be added together in this way of talking about things. I have one region, each one has its own private quadrant, and it's just meaningless to talk about how I would relate them one to the other. Is that clear? All right. But let's just pause here for a moment. This is the standard way of writing Schwinger parameterization, as sort of independent propagators. Of course, I could do a linear transformation on alpha and beta and write exactly this expression in a number of different ways, okay? For example, I could have it look so that alpha looks like this over this quadrant. Well, that's sort of trivial. I just change the sign in what I mean. Maybe slightly more interesting, you see, I can just linearly transform any wedge-shaped region to any other wedge-shaped region, okay? So, for instance, I could also write exactly the same single term as an integral over something like this. Okay? How would I write as an integral over something like this? So let's say this is the vector 1, 1. This is vector 1, 0, right? Then what am I doing? I want to write any point inside here. So let me call this space t space, okay? I can write any point inside here, any t. I can write as alpha times 1, 0 plus beta times 1, 1, right? Where alpha and beta are positive. It's a linear combination, positive linear combination of this and that, right? And so what I want to do is integral d alpha d beta from 0 to infinity, e to the minus, alpha x13 plus beta x14, say. I can now rewrite this in terms of t. Okay, so now we can switch back and forth between t and alpha and beta. So, t1, t2 is equal to alpha 1, 0 plus beta 1, 1. So that tells me that t1 is equal to, that t2 equals beta, t1 equals alpha plus beta. So, sorry, what am I? Oh, sorry, I want to solve for alpha and beta. So beta is t2, and alpha is t2 minus, is t1 minus t2. So I could rewrite this expression as the integral over this wedge now in t space, dt1, dt2, e to the minus alpha is t1 minus t2, so it's e to the minus t1 minus t2 times x13 plus beta is just t2 plus t2 x14. Is that clear? All right, so there's nothing sacrosanct about the positive quadrant. Okay, it's just the wedge. All that matters is it's a wedge, and so I can linearly transform that wedge into other wedges. Okay, of course, if I do it in a wedge like this, the numerator will also always look like t dot something, of course, but you have to do the linear transformation back and forth between between the wedge and the standard wedge, if you like, in order to see it. Okay, so this is just giving you a little bit of inspiration now that a single diagram can be represented as an integral over a wedge in various ways. All right. Now I think it's clear what we're going to do. Okay? Because now, unlike this idiot thing, where we're going to take every diagram and add them together and say, oh, we did something Biff-like, right? Now we're going to do, apologies to any Biffs on Zoom. Now there's something here which is sort of begging to be done. You see, I have this picture where this is a diagram. This is another diagram. This is another diagram. They're all diagrams, right? So what I want to do is write down an expression which gives me an expression which is an integral. So what am I looking for? I want an integral over the entire space now, not 0 to infinity. So this is going to be my t space now, t1 and t2. I'm just calling them t's, right? I want to have something like this, and something that's going to be e to the power of, and here I think I'm going to switch convention. Here I'm putting a minus sign everywhere. Here I'm going to put a plus sign, and the alphas will then have to be negative, okay? I think that's consistent with what I'm doing elsewhere. But I want to put some alpha 1, 3, which is going to depend on t1 and t2, okay? Times x1, 3, plus alpha 1, 4, that will depend on t1 and t2, times x1, 4, plus all the rest of them. Okay? That's what I want to put in. In other words, I want to put in an integral d squared t e to the power of the sum over all the curves x of some alpha x, which is now not a variable. My variables are the t's. The alpha x are going to be functions of the t's times the corresponding x. But what is the purpose of life of these functions? These functions have to turn into what would give me Schwinger parameterization in that wedge. Okay? Now we've learned what Schwinger parameterization looks like in every wedge, right? I know what Schwinger parameterization should be in every wedge, so I just have to write down some alpha that's going to turn into the Schwinger parameterization. So what does this alpha have to do? For example, alpha 1, 3, so let's go back. So for example, alpha 1, 3 of t, it should have the property that it's only non-zero in this cone and in this cone. And otherwise it's 0, right? Because I want alpha 1, 3 to only turn on either in this cone or in that cone, where 1, 3 exists. Alpha 1, 4 will only be non-zero. Will only be non-zero in this cone and that cone, and 0 everywhere else. So alpha 1, 3 and alpha 1, 4 will both be non-zero only in this cone. So in this cone, this big sum will only have alpha 1, 3 and alpha 1, 4. In this cone, it will only have alpha 1, 3 and alpha 3, 5. In this cone, it will only have alpha 1, 4 and alpha 2, 4. But the function of alpha 1, 4 and alpha 2, 4 that it will be in here will be exactly that guy. Right? Will be exactly that guy in order for this to turn into the Schwinger parameterization for the diagram 1 over x1, 4, 1 over x2, 4. Okay? So is it clear what we're trying to do and why this is called global Schwinger parameterization? What I'm doing is introducing, not integrating over the Schwinger parameters themselves. I have this sort of auxiliary space where the fan lives. Okay? So the space is, what's the dimensionality? Is the number of propagators in the diagram. That's the dimensionality of the space that we're talking about. But we're looking for functions on this space that have the property that they're piecewise linear. Notice this is a crucial thing. The alphas there are linear functions of the t's. Okay? But they're not linear everywhere. In every cone, they're one linear function. Okay, so alpha 1, 3 is going to be some linear function here, some linear function there, and it's going to be 0 here, 0 there, 0 there. Okay? That's what we're after now. Piecewise linear functions, which have the property that they turn into the Schwinger parameter for each ray in every cone. Okay? All right. Now, we can immediately translate this into a requirement on the function itself. What we need is that, so for any x, for any curve x, by the way, everything I'm saying here is true for a random surface, any surface. We're going to be illustrating continually with this example, okay, but it's true for any surface. For any x, we're looking for a function alpha x that depends on this sort of space. The T space is just the space where all the G vectors live. All the G vectors are drawn. We're looking for a function alpha x of t, which is piecewise linear on all the cones. And it needs to satisfy the following magical property. Alpha x evaluated on the G vector for any other curve y has to be minus delta xy. All right, now let's think about why that's what we're trying to do. You see, if alpha has this property, then that means that if I look at, okay, so let me say again, the function is piecewise linear, and I'm asking it for it to equal something somewhere, right? I'm asking it to be on the ray for x itself, it should be -1. On all the other rays, it should be 0. That information, together with it being piecewise linear on the cone, completely determines what it has to be everywhere. Okay? I'll leave it as a little exercise for you to write down the explicit formula, but we'll just do it in this example in a second. But let's see why this is what we want. Because if I'm now integrating, dnt in general, and I have e to the sum over x, alpha x of t, x, this is a linear expression. The alphas are linear, so this is a piecewise linear expression, right? Since it's piecewise linear, that means that inside any given cone, it's just flat out linear in that cone, by assumption. Because it's flat out linear, in this cone, I can express it as a linear combination. If I take any point t inside, and I write this point t inside as like alpha 1, the G vector for 1, let's say in this example, plus alpha 2, the G vector for 2, plus ... Let me not call it alphas, sorry. I don't know, beta 1, G1, plus beta 2, G2, plus ... Because it's piecewise linear, this function, this linear function, let's call it an action, okay? Then S is just going to equal beta 1 times the value for x evaluated on the G vector 1, plus beta 2 times the value of S valued on G vector 2, and so on. That's what linearity means, right? Inside the cone, it's linear. So this is what it means. And then the fact that alpha on the G vector gives you -1 and 0 on all the other ones means that this is exactly negative beta 1 times x1, negative beta 2, x2, etc. All right? So that's what the action is. So the integral over this cone is then the integral over dnt over this cone is then the integral d beta, dn beta, e to the minus beta 1 x1 plus ... But now the betas are just from 0 to infinity, and there's a tiny Jacobian, right? What is the Jacobian of the change of variables between these t's and the betas? It's the determinant of the G vectors. Okay, so I have to multiply by the determinant of the G vectors, G vector for 1 up to G vector for n, capital N, but this is exactly the thing which is 1, we just said. Okay, all these G vector determinants are 1. And so this is exactly, sorry for such a messy board, this is exactly 1 over x1 through xn. So that's exactly the Schwinger parameterization, okay? So if we summarize then, we can write the amplitude as an integral over a single object. Now we can write the amplitude. It's already slightly cool. We can write the amplitude as the integral d capital NT e to the sum of alpha x of t times x, the sum over all the curves. Okay? Where these alpha x's are determined by being what I wrote there. Alpha x are determined by being piecewise linear on the cones and satisfying the magical fact that alpha x on gy, is minus delta xy. Okay? So is it clear that this is less dumb than before, right? Now we're leveraging the fact that there is this fan, the cones all fit together. This is, it relies on the fact that the g-vector determinants are all 1, and so on. All right. Let's actually explicitly build what these alphas look like in our little example, okay? And as I said, there's a formula you can write down explicitly for the alphas in any cone, okay? It's just a linear algebra exercise. It's a formula involving determinants and the inverse of the matrix made of the g's in any cone. But instead of just writing down the formula, let's just work it out by hand in this example, okay? So it's pretty easy to work out by hand in this example. Yes? Yes, but the magnitude is what shows up in the Jacobian, right? When you do integration changes, it's the magnitude of the Jacobian which shows up, okay? So I'm going to call this direction T1 and this direction T2. I could have called it, let me call it T13 and T14, okay? Just because it sort of lines up with these directions. Okay, so what does alpha 1,3 of T look like? So remember, the job of alpha 1,3 of T is it has to equal minus 1 here. It has to equal 0 here on all the other guys, right? Only has to equal minus 1 on itself. It has to equal 0 everywhere else. Okay, so, and it has to be piecewise linear. So, well, what could it be? Just minus T1 here, minus T13, minus T13. Okay? Is that clear? If I evaluated on 1, 0, I get minus 1. But T13 evaluated here is 0. Evaluated here is 0. And of course, it's equal to 0 here, too, right? And this function is piecewise linear. Definitely is, the derivative is discontinuous for sure, but the function is continuous. So I should have said that. It's continuous and piecewise linear, okay? All right, is this clear? Is this clear? This is doing what we want, okay? All right, so let's look at, so a slightly more fun example. Let's look at, and I'll leave it for you to do the rest. Let's look at alpha 2,4. Okay, what is alpha 2,4? This is something that's got to equal minus 1 here and 0 here, okay? So for it to equal minus 1 here and 0 here and here, in here, it's going to equal T1. And over here, it's going to equal minus T2. Okay? So let's stare at that for a second, right? So that means that on this line, on minus 1, 1, T1 is equal to minus 1. Minus T2 is equal to minus 1. So that's good. This is equal to minus 1 there. Sorry? Oh, sorry, T13. Fuck. T14. Thank you. Okay? Thank you very much. Okay? Does that make sense? So then T13 is 0 here, T14 is 0 there. This is piecewise linear, it's continuous, and it's equal to 0 everywhere else. All right? And now you can really have fun. You can go and just work out sum of alpha 13, x13, alpha 14, x14, so on, and you'll just see in every cone, I get some linear expression, and the linear expression is exactly the one where you integrate in that cone, you're going to get 1 over xx. Okay? So this is global Schwinger parameterization. And to find global Schwinger parameterization, we need to find global Schwinger parameterization, we need to find these functions that do this magical thing. Okay? Now, this is all great. And what I told you, you could actually imagine applying to a random fan. So let's say someone gave you a totally random fan. That means they gave you a collection of rays, they grouped them into cones, and they said, these are what I'm going to call Feynman diagrams. It has nothing to do with Feynman diagrams, right? What I'm going to call them Feynman diagrams. The object I care about is the product. I'm going to associate an x with every ray. The object I care about is the product of all the 1 over x's for all the cones, and I add them all up. That's what I'm going to call an amplitude. That's what I care about. But they pulled the fan out of their ass, right? So some totally random fan, okay? You could say all of these words. Do all of this. There's a global Schwinger parameterization for all of these things. What's the difficulty? The difficulty is that finding these alpha x of t's is naively as difficult as enumerating all the Feynman diagrams. Okay? After all, think about what knowing this alpha x of t tells you. So first of all, how do you determine it? It's piecewise linear. So you have to go to any cone. We have to do just what we did, right? We did it in this example. We go to any cone. In any cone, we see what it has to do, and we determine it. So there's a formula for it, some explicit formula for it, but it's a cone-by-cone formula. Okay? So the naive way of determining it is as complicated as enumerating all the Feynman diagrams. And if we go back to something I said yesterday, one of the, I don't usually like this sort of computational complexity language. It's a little heavy and pretentious for my liking. But it is a fact that while the number of variables, the number of propagators scales like n squared, right? For example, at tree level, we said it was nn minus 3 over 2, but it's roughly n squared. The number of diagrams is scaling exponentially, like 4 to the n. Okay, so the number of cones is exploding exponentially, even though the space is only growing moderately in size. The space is growing like n minus 3 dimensional. The number of rays is like n squared, but the number of cones that you make out of them is exploding exponentially. Okay? So that means that this direct way of determining the alphas is literally as complicated as enumerating Feynman diagrams. Okay? So we're still not winning over Feynman diagrams. And this is what you would do if you had totally random fan, is you would have, you could say all of these things and you would not win. All right? So this is as far as we can come with very purely elementary statements. In the neighborhood of just staring at the curves, projecting, all of these super simple things. Now there's a second bit of magic, and this second bit of magic is more new. So, I haven't said anything about references or anything like that, but I'll say sort of very roughly that this first part of the story, that there's a fan, that the fan covers the whole space, et cetera, this in various versions goes back to Thurston's work on hyperbolic geometry, part of it, and then in a more modern, more complete context, including boundary curves, it showed up in the story of higher Teichmuller theory and surface cluster algebras. People like Fomin, Zalvinsky, Dylan Thurston's son, and Fock and Goncharov in the mid-2000s. And then it's been going on since, I think, in the form that we're using it today, including everything about closed curves and all the rest of it. That's something that, a very tiny little bit that we're adding to the story. But this is a magic that's been appreciated for a while. What I'm now telling you is more new. Okay? And various contexts have been seen, parts of it have been seen going back to the very early literature on string theory in the 60s. But the full generality is really quite new. Right, so now what we're going to do is tell you where these alphas come from. Okay, I'm now going to give you a formula for the alphas. And what's fascinating is that we're now going to find a formula, so we're going to get a formula for alphas. And remember, you would naively think that what alphas are knows not just about x, but about all the other curves in town, right? Because alpha has got to do this job, that it cares, it's going to light up me, it's not going to light up anybody else, right? It's got to be linear on this count. Clearly, it should care a lot about all the curves in the problem, right? That's why naively we have to build it cone by cone. That's why there's a concrete formula for it that you can write down as a linear algebra exercise, cone by cone. It's not just something that depends on capital X. It has a different function in every cone, right? So you'd think naively it cares about all the other curves. Even though our action doesn't care about, our action is just a sum over all the x's. The x's are all treated independently. It's either the sum over all the alpha xx or the product of all the e to the alpha xx, depending on how you think about it, but they're all independent. And the action, they're totally independent, right? So we have this formula, again, a equals integral dnt e to the sum over x alpha xx. So here, they all seem independent, but the functions surely care about all the other curves, right? That's what you would naively think. So the second little miracle in the subject is that there's a formula for alpha x purely in terms of the word for x. Okay? There's just going to be a word for x. You start the word for x, you're going to write down a formula for alpha x. Does not care at all about the other curves. Purely local about the word x itself. Okay? And to do this, it's actually going to be associated with a counting problem. Now, I have an hour and 15 minutes, and if I had maybe 3 hours and 15 minutes, I could tell you where this counting problem comes from, okay? So we're just gonna write down the word. I'm just gonna give you a counting problem. Very simple looking counting problem, and then we're gonna solve the counting problem, okay? But it'll look like this counting problem I'm just pulling out of nowhere a little bit. It's not a hard counting problem, but it'll look, you wonder why you care about this counting problem and not another counting problem. In a slightly longer way of going back to the conceptual underpinnings of this stuff, it comes, this whole subject of thinking about the surfaces and the diagrams and the fact graphs and all the rest of it is actually deeply connected to the representation theories associated with quivers, quiver representation theories and the categories of quiver representations. And I'm a dyed-in-the-wool theoretical physicist who thought not once in my life would category theory matter 1 epsilon to my existence, and I was completely wrong, okay? That there is something in this world which has beef, not just bullshit about drawing arrows between things that I could do without saying the word category, but which actually has real content and real juicy formulas that I would not have thought of myself, okay? If I had longer, I would tell you where it comes from and how it's related to the category of quiver representations, and that's an extremely beautiful story by itself, which is not just a story, but tells you how to generalize these things beyond surfaces. Okay, so there's a richer class of mathematical objects that have many similar properties, have many similarities to amplitudes, but are not quite amplitudes, which are associated with these generalizations. So for that, you really need to understand the connection to quiver representation theory. If you've heard anything about this amplitude stuff before, you may have heard about cluster algebras related to this stuff. If you haven't heard about it, never mind. The cluster algebras turned out to be very close to the correct idea, but not quite the correct idea. And the really correct idea is the quiver representation theory. That took us like a year and a half to understand. But anyway, so there is a rational origin for all this. It's very beautiful. I would love to tell you more about it, but I'm not going to be able to tell you about it. Instead, I'll just define the problem. The problem is so simple and nice, you won't hate it, okay? It's not a crazily ugly problem. You'll just wonder why it has anything to do with anything, okay? All right, so that's one apology. The other apology is I'm not going to be able to prove anything in the time that I have. Okay, I will try to define the object and tell you what you do with it. And we're going to do two things with it, one of which will give us string amplitudes, the other one will give us field theory amplitudes. Okay? But mainly, we're going to see how this thing solves our problem of finding global Schwinger parameters. All right? So, here's what we're going to do. So remember, every curve is associated with a word. So we have these things like 1, 2, down, 1, 3, up. I don't know, 1, 2, up, 1, 3, down, 1, 4, 4, 5, and so on, right? So we have words like this. Let's, for the moment, forget about all these. Let's just talk about totally general words of this sort. So A, down B, up C, down D, E, F, G, H. Totally random word like this. All right? Associated with such a word, I'm going to define a counting problem. And the counting problem is going to be associated with what I like to call the relationships with baggage generating function. Okay? Relationships with baggage generating function. So before defining it formally, let me say what we do, for example, let's say this is your word. Okay? The counting problem is I just want to choose any of these letters. All right? So I can choose none of them. If I choose none of them, I write down 1. Okay? I can choose the letter A, so I'd write down plus A. I can just choose the letter C. I can write down C. I can choose A and C together. I'd write down AC. But here's the relationships with baggage part. You're supposed to think of this picture, this mountainscape, also think about it as something with a causal structure. Right? So the idea is that if you choose anyone, you have to choose everyone else in their past like cone. So that's the sense in which it's like a relationship with baggage. You know, you like meet someone, you start going out with them, you're kind of dating everyone else that they've ever dated at the same time, right? You know, so it's relationships with the baggage. Okay? So in other words, if you choose B, you must also choose A and C. You can't just choose B alone. If you choose B, you have to choose A and C. A and C are on the past like cone of B. If you think about these 45-degree lines as defining like cones, okay? So you'd have plus BAC. Okay, is that clear? Should we do another example? So let's say it's the other way. Let's say we had A down B up C. Then I can choose nothing. I can choose B. I can choose A, but if I choose A, I must choose B. I can choose C, but if I choose C, I also must choose B. And if I choose A and C, then again, I also just must choose B. Okay? All right. Now, there's a very nice way of actually, given any word, of actually solving for the generating function. Okay? And you can do it recursively. So the idea is very simple. Imagine that you start from the left. And let's say you start from the left and you have some variable here, a. And let's say you're going up, right? So let's say you're going up from a, and then you have the whole rest of the word, okay? What I'm going to do is I'm going to divide all the things that I can have into either I choose a, yes, or I don't choose a, no. So I'm going to have, so if this whole object is f, these things are called f polynomials associated with given word. I'm going to break the f's up into f equals f no of a plus f yes of a, right? Which means that either I do include a or I don't include a, right? Okay, so now let's think, what does f no and f yes look like? And then the rest is going to have its own. So a is maybe attached to some b here, which does its own thing. Okay? And b itself would have some f yes and f no that depends, that does or doesn't include b. So I'll call that lowercase f, just to remind myself that the uppercase f is about a, the lowercase f is about the rest of the word b. All right, so what is f yes of a? So this is the case where I'm going up from a. So this is the up case. I'm going up from a. What is f yes of a? Well, if I'm choosing a, then I'm going to multiply by a, right? I'm going to have a. But in the rest, what am I going to have in the rest? Well, if I choose A, nothing obliges me to choose B, right? So I can't either choose B or not choose B. I don't care either way, right? So this is A times little f yes plus little f no. Doesn't care whether I choose B or not. Is that clear? Meanwhile, what is f no of A? F no of A is a little more interesting. F no of A, I'm not choosing A, right? But if I'm not choosing A, it means I can also not choose B. Because if I chose B, I'll be forced to choose A, right? So f no of A is little f no. There's no f yes. All right? What if we're going down? Yes? No. If I choose B, I must choose A and C. It's only the past like cone of B. That's right. If I choose A, yeah. Is that clear? Okay. Okay. All right, what if I'm going down? So I'm going A down to some word here that has B and so on. Well, now, F yes, if I include A, then what happens? I have to have A, but I must include B. So this is F yes, little f yes. Meanwhile, if I don't include A, F no, this is, well, I can do anything. I can include A, I can or can't include B. So it's little f no plus little f yes. Okay, is that clear? Okay, but that means that I can build f recursively because there's just a matrix that takes me from the left to the right. So let's say in the case where it's up, so when it's going up, it goes A up, right? There's F yes, F no is equal to A0, 1, little f yes, and little f no. Okay, that's what we learned from the right board. And when it's down, we have that f yes and f no is equal to A0, 1, 1, little f yes and little f no. And so you can keep going, right, until you get to the last letter, just multiplying these matrices as you go. And what do you get for the very last letter if you just have a last letter A? F yes is A, F no is 1. Okay? So if you have a word, any old word, if you have a word A1, A2, A3, A4, whatever it is, AN, then I have M up or down of A1, M up or down, whichever it is, of A2. I just multiply these matrices up to the second to the last one, this last up or down, AN minus 1, up or down, of AN minus 1. And the very last thing is just AN 1. Because F yes would be AN and F no would be 1. Okay? So this gives me the F yes and F no. And then I can just add F yes and F no to get the full F for the whole thing. All right? Or if you want, you could even represent this last thing just by convention. You could always say that you're ending by going up, and then you write it as M up of AN minus 1 of AN multiplied by the vector 0, 1. Okay? That's just a purely conventional thing. And then the F would be 1, 1 times just the big matrix M times 0, 1. Okay? Okay, so this is the concrete way of solving for the for this relationships with baggage generating function in terms of a product of a bunch of 2x2 matrices. We could apply it to these examples and see that it works, but anyway, let's. All right. Now, let's go and think about what our actual words look like. Even at tree level, it's sort of natural to break our actual words up into pieces. So, any word that we have actually starts with a boundary component, right? And ends with a boundary component. It might go off spiral to infinity, in which case the boundary component is at infinity. But anyway, it starts with something and goes up or down, and it ends with something up or down at some beta, right? So it's natural, because we have these boundaries at the end, it's natural in thinking about the relationship with baggage generating function to just keep track of how it depends on the boundary pieces, right? So there are 4 terms that it could have. If you look at the full F that you get, there are 4 terms that it could have. It could have a piece which does have alpha and does have beta, does have alpha, doesn't have beta, doesn't have alpha, does have beta, doesn't have alpha, doesn't have beta. Right? So there are sort of 4 different things. So this is another yes, no. You can have S, yes, no for alpha, and F, yes, no for a beta. In other words, the full F can look like some alpha, beta, F, yes, yes, plus alpha, F, yes, no, plus beta, F, no, yes, plus nothing, F, 1, F, no, no. Where this yes and no depends on whether it does have yes alpha for the first one and yes or no beta for the second one. Okay? So clearly it's natural, since we have these boundaries at the end, it's sort of natural to divide things up in this way. And it's very, very simple to see just from these matrices that I defined, that those 4 Fs are actually directly computed by the word as well. So if I have, let's say I had alpha up, A, down, B, C, D, E, beta, then first of all, what's the matrix that I'm supposed to associate with this, right? For the word. So there's a matrix associated with the word, which is a matrix associated with the word, which would be M up of alpha, M down of A, M up B, M down C, M down D, M up E, right? That's the matrix that we just talked about. Alpha is a boundary. All the other guys, we have variables naturally associated with them. We have not talked about variables associated with the boundary. So it's actually natural to put this boundary variable equal to 1. Right? And it's an extremely simple exercise in just thinking about what this counting problem is, to see that this big matrix, MW, this 2 by 2 matrix, that I naturally associated with the word, is actually exactly given by F yes, yes, F yes, no, F no, yes, F no, no. Okay? So I'm saying all to say that once you have the boundaries around, it's actually natural to take all the information in this 2 by 2 matrix. Okay? What we did before is dot it into 1, 1 and 0, 1. But actually, when you have the boundaries around, it's the entire the whole 2 by 2 matrix has information. Okay? And the information it contains is how to divide up the counting problem into the yes-nos that depend on the boundary curves. Okay? Who's unhappy at this point? A little bit unhappy, right? You know, so where did this problem come from? Well, okay, I'm sorry. Okay, but there's one kind of cool thing that we can, one very simple, quick thing that we can see from these curves already. Let's take the determinant of this matrix associated with this word. Yes? Oh, it's not block diagonal. Yeah, that's just the interpretation. That's right. It's a 2 by 2 matrix, right? It's a 2 by 2 matrix, and I'm just telling you that the interpretation of each one of these blocks is, in fact, the F. Yeah, so this would be alpha beta, right? So except I'm putting alpha to 1, okay? So it would be, so this would be the alpha beta part, this would be the alpha part, the beta part, and the nothing part, okay? So, I mean, I could have also said, just look at this big word, but I defined these matrices by the desire to solve this counting problem, but then we didn't use all the information in the matrix, right? We should have dotted into 1, 0, 0, 1, and 1, 1. But I'm saying when we have boundaries, in fact, all the information means something. Okay, all the information has some content about the counting problem for the parts that we care about, right? The part that, okay? I could have just told you to multiply these matrices together, and then that would have seemed even stranger. Where the hell do these matrices come from? Why am I multiplying them, and so on? If I had longer to prove where things come from, the counting problem is the more primitive thing that lets you understand the magical properties of the variables that we're going to talk about. Okay? The 2 by 2 matrices are the most efficient way of computing them, but the sort of the conceptual understanding of the counting problem is what makes the fact that they do what they do more manifest. So it's useful to have both points of view. But anyway, I'm not explaining that. So what is this determinant? Well, it's just the product of all the determinants of these matrices. But the determinant of all these matrices is really simple. It's just A, right? It's either A01 or A011. All the determinants are A. So this is just the product over all the A's. And in particular, if we imagine that all these variables, all these A's are positive, later I'm going to call them Y's. I don't know why I was calling them A's here. Okay? If we imagine all these variables are positive, then this is always positive. So this means that f yes, yes, f no, no, minus f yes, no, f no, yes, is a positive number. Product over all the a's is positive. And our last step is to use this fact to define an interesting ratio that's always between 0 and 1. Okay, this says that always this number is bigger than that number. So with any curve x, any arc x, I'm going to define a variable u sub x, which is equal to the f yes no, f no yes, divided by f yes yes, f no no, for the word associated with x. Okay, so the last 15 minutes have been maybe a little painful, but I hope you see some super concrete thing, right? Give me a curve, I write down the word, multiply a bunch of these matrices, and I define a variable that's between 0 and 1, associated with every word. So it's clear this u is between 0 and 1. All right. So let's do a little example. Well, let me just tell you, let's do a little example. So if we go back to our 5-point problem, let's look at this curve 1, 3. That curve 1, 3 was 1, 2, down 1, 3, up 3, 4, right? So what is the matrix in this case? It's m down, and now I'm going to call all the variables y, okay? So y, 1, 3, y, 3, everything y. So it's m down from 1, 2 that I'm setting to 1, remember. The boundary I'm setting to 1. And then m up of y, 1, 3. Okay, so what is this? Remember, m down, I'll write again, m up of y is y, y, 0, 1. And m down of y is y, 0, 1, 1. Okay, so this guy, this is our matrix, this is our word. This is m down of y is 1, 0, 1, 1. M up of y, 1, 3 is y, 1, 3, y, 1, 3, 0, 1. So this is equal to y, 1, 3, y, 1, 3, y, 1, 3, and 1 plus y, 1, 3. Okay? That's our matrix. And so what is u for 1, 3? U for 1, 3 is always sort of BD over AC. Okay? So this is going to be y, 1, 3 over 1 plus y, 1, 3. Okay, very nicely, it's between 0 and 1. All right, let's do another example. Okay, it's going to force me to multiply more 2 by 2 matrices, but they're not so bad, the 2 by 2 matrices. So let's say we do 2, 4, the hardest one. Everything's not too hard here. So 1, 2, 3, 4, 5. 2, 4 is this guy. So this one was 2, 3, up 1, 3, down 1, 4, up 4, 5. So this is going to be m up of 1, m down of y, 1, 3, m down, m up of y, 1, 4. So this is 1, 0, 1, 1. Oh, fuck, no. M1, 1, 1, 0, 1. y13011, y14, y1401. So let's multiply these two out first. So this is 1101, y13, y14. This is to prove that I can multiply in real time, which is actually somewhat impressive. y14. Hey, don't laugh. You try doing it up here, guys. Geez, that's a little bit nerve-wracking. And then this is equal to, I'm a multiplying God. Look at that. y13, y14 plus y14. Let's make it a little bit bigger so I'm more godlike. y13, y14, 1 plus y14 plus y13, y14. And y14, and 1 plus y14. Okay, so that's our matrix. And so U24 is equal to, again, it's this over that. This is factors out of y14 times 1 plus y13. So U24 is 1 plus y14 plus y14, y13 over 1 plus y14, 1 plus y13. Right? And once again, this is between 0 and 1, right? Because if you multiply it out the denominator, it has everything upstairs, but also plus y13. Okay, so the denominator is bigger than the numerator. And so this is between 0 and 1. All right. Okay, so now let me just write out what the remaining three are. Let me just write them all down on this board. Oh. So we have U13 is Y13. These are the ones that we wrote out before, but I'm just going to write them all down. U14 is Y14 1 plus Y13. Actually, I know these off by heart. I don't remember the matrices off by heart, but I remember these off by heart. Okay, see, these are the 5 y's, and they're all between 0 and 1. All right. Okay, these are amazing objects. So this is now going to be, now we're going to spend our remaining 45 minutes just learning things about these, U's. Okay. The first thing we're going to observe is we're going to imagine these y's are all positive numbers. Okay, so we're going to imagine all the y's are positive. If all the y's are positive, just means y13, y14. Okay, so y13, y14 is positive. Then we know that all the u's are between 0 and 1. But you'll notice that the u's can go to 0 and 1 in various ways. For example, if y13 goes to 0, then u13 can go to 0, right? That's fine. But how, for example, can I get how can I get u24 to go to 0, right? U24 going to 0 is not any of the y's going to 0s. When y's go to 0, the U24 goes to 1, right? But there are some interesting directions that you can take off in y14 or y13 space. Okay, so for example, if I make y14, if I make y13 go to infinity, right? And y14 go to 0, then if I make them go off to 0 infinity in various rates, I can make the U24 go to 0. Okay, we're actually going to see this all more explicitly in a second. But you can already play with this. And if you look at the y's, that by sending the y's to 0 to infinity in different rates, you can actually set different u's to 0. Okay, so the u's are bounded between 0 and 1. That's obvious. We can also reach all the boundaries, all the 0s and 1s together, right? But already just if these formulas, if you experiment with this, you'll discover something really interesting, that I can, for example, send U13 to 0 and U14 to 0 at the same time. If I send U13 and U14 to 0, all the other u's will go to 1. Okay? However, I can't send U13 to 0. If I just send U13 to 0, U24 must go to 1. Okay? So 1,3 and 2,4 are crossing chords. And if I send 1,3 to 0, all the chords that cross it just go to 1. Right? So this is what we call a binary geometry. This is an even stronger realization of the combinatorics of compatibility that we saw from the icosahedron. In the icosahedron, we have some polytope, and it keeps the incompatible facets apart from each other. Here, we have some curvy variables. See, these are nonlinear expressions, but they have an even more remarkable feature, that if you send the variable associated with some x to 0, all the incompatible ones go to 1. It's not that they don't meet it somewhere. It's like literally binary. It's either 0 or 1. Okay? The incompatible ones go to 1. We're going to explain where this comes from in a second, where we talk more about the nonlinear features of these u's. But the first thing that I want to do is actually more systematically understand, what do these u's look like as I go off to infinity in y space in different ways? 0 and infinity in different ways. Okay? So we're going to do that. And this entire topic, you see, these u's are ratios of polynomials. And I want to understand what they look like as the various terms in the polynomials go to 0 and infinity at different rates. The entire subject of understanding what polynomials or ratios of polynomials look like in this limit as you take the variable to 0 and infinity is called tropical geometry. And what we're going to do is called tropicalizing this function. Okay, just so you have an idea of the meaning. Sorry, not of the meaning, of the origin of the phrase. Okay, so, yes? No, it's not. No, it's almost. So it's not quite. It has a geometric interpretation in hyperbolic geometry, but it's not directly in terms of angles. There are certain cross ratios. So I've described a way of thinking about these things in terms of a counting problem. There is another way of talking about exactly the same u's in terms of distances and cross ratios in hyperbolic geometry. This second way of thinking about it in hyperbolic geometry is more closely related to the things that you're used to seeing in the worldsheet and string theory. There's also this way that has nothing to do with the worldsheet, and this way is in many ways more fundamental. It's more primitive, the counting problem is easier, it generalizes, and you learn more things by thinking in the counting problem way than you do thinking in the other way. But it's not quite angles. They are certain cross ratios, but they're not really angles. All right, so let's say in general, but we'll do it with these things. Since the y's are between 0 and infinity, I'm just going to write y13 is e to the, I'm going to write y13 is e to the minus t13, and y14 is e to the minus t14. Okay? Yes? Oh, it was just relationships with baggage problem. We're just counting the number of ways of choosing each letter with this relationships with baggage rule. That if I choose a letter, I have to choose everyone in their past like code, right? So that's it. That's the counting problem associated with every word. So there's the curves. From the curves, we get a word, and then there's this counting problem associated with the word. Yeah. Yes. Well, I mean, it tells you exactly how many different ways are there of doing this, right? So yeah. So if you want it, if you could do that, it would be the total number, but it's giving you, the generating function is giving you all the refined information there is in this question. Okay? And in the examples, all the coefficients were 1. Sometimes the coefficient can be more complicated. So you have more interesting words, longer, the same variables can occur in a number of times, and so then you get more interesting coefficients in front. They're not always 1. Okay? Okay. They're counting in, I'll just say these words if they mean anything to you, if not, just ignore it. They're counting representations. So these pictures are associated with certain. Let me not say it. Yeah, it won't be helpful. All right. So yes. Yes. Oh yes, absolutely. Very, very much so. So this is not a coincidence. This is not a coincidence at all. But in general, they're not weight spaces, but there's a very special class of these quivers that have some finiteness properties, the kind of simplest versions. And in that case, there are the weight diagrams associated with corresponding Lie algebras. So they're very closely connected. So that in the cases where the quivers are Dynkin diagrams, then there's some finiteness. The surfaces are, anyway, there's some canonical, simplest example, but in general, it's not like that. But it's not a coincidence that this looks like a weight diagram at all. Yeah, I would take another hour to explain that connection, but it's not, it's definitely a correct connection. Okay? All right, so I'm just parameterizing the y's like this, and now the t's can run from 0 to infinity, right? So the y's just have to be between, sorry, the t's can run everywhere over the entire space. The y's just have to be between 0 and infinity, but the t's can run everywhere. All right? And now, so all the different ways in T space, I'm not drawing any fan or anything. In T space, in T13, T14 space, all the different ways of going for the y's go to 0 to infinity in different rates are showing up in, just different directions that I can go out to infinity here, right? So let's say you had some expression. Let's say you have some expression. I don't know, let's take a slightly juicy one, like this one, okay? Let's say you have an expression, y14. I just want to see, what does it look like? In all the different ways I can send the y's to 0 to infinity, what can this expression possibly look like? Well, what would I do? Let's just take that expression, but you'll immediately see it has nothing to do with these particular polynomials. You can do it for totally random polynomials. But if I have y14, 1 plus y13 over 1 plus y14, plus y14, y13. Okay, well, what does this look like? So I'm just rewriting this. This is e to the minus t14, 1 plus e to the minus t13 over 1 plus e to the minus t14 plus e to the minus t14 minus t13. Okay, I've just written it out. But now what I want to know is, how does this thing behave as I go to infinity in a particular direction in T space? So I'm going to write T like T13, T14. This is my vector T. I'm going to write this as some rho times T hat, some particular direction. And I want to send rho to infinity. And I want to see, what do these expressions look like as I go to infinity, right? Now, let's say T has just some totally generic direction. I'm going to infinity. What's going to happen? As I go to infinity, okay, this term is what it is what it is. But in this term, as I go to infinity, either this is going to dominate or that's going to dominate, right? So as I go to infinity, this is either going to equal 1 or it's going to equal e to the minus t13, depending on whether t13 is, whether t13 is bigger or less than 0. Okay? Similarly, down here, it's going to look like either 1 or t14 or t14 plus t13, just depending on which one of these exponents is bigger. All right? And so the answer looks like something very nice. The answer as I go to infinity, at infinity, u goes to something that you can call e to the tropicalized u. Okay? Where u trop is given by the following expression. So u trop is equal to, so it's e to the, so u is, everything is going to an exponential, because just one monomial is going to dominate. In any direction, this is going to be e to the something, right? It's going to be e to the t14 and either minus t13 or not. And down here, minus either nothing or minus t14 or minus t14 or minus t13, okay? So it's all going to be the exponential of something. That's why I put it in the exponential. But what is this thing? Well, from this term, it's minus t14. That's just always there. But from the next term, what am I going to have? I'm going to have plus the max of 0 and minus t13. Right? So whichever one is bigger is going to be the thing which dominates in the exponent. Right? And then I'm dividing, so it's going to be minus something. It's going to be minus the max of 0 and minus t14 and minus t14 minus t13. Okay? You see, what's cool about this is that we're taking a nonlinear complicated object, right? But as we go to infinity, we're linearizing it as much as possible. Right? As we go to infinity, the nonlinear complexities cancel out, and I get something which is piecewise linear at infinity. Okay? And this is the piecewise linear expression which I get. So in general, you can do this for any polynomials, any product, polynomials to any powers, and tropicalizing it is simply the following. The operation of multiply turns into add, and the operation of add turns into max. Okay? Just like we saw here. And, oh, by the way, and the coefficients don't matter. The coefficient in front of the polynomial, I mean, here they're all 1 anyway, but the coefficients don't matter because we're just looking at what's in the exponent, the leading thing in the exponent. All right? We could say a lot more about this, but I just want to get to some punchlines for you. So we have defined with any curve this nice variable u sub x that's between 0 and 1. When I write the y as e to the minus t, now the t can range over the entire space. As I go off into infinity and t in different directions, the u's turn into the exponential of their tropical friends, which are piecewise linear functions. Okay? Well, so now you're not going to be surprised that I'm going to give you a formula for the magical alpha x that we needed before. Right? We needed alpha x. What is alpha x? It's just the tropical ux. Let's see that it works in a moment, but let me stress what's amazing about this formula. We only talked about the curve x. We haven't mentioned any other curves. Okay? And yet this thing knows to give me the answer that lights up one ray, right? I forgot to say, what are some other things these alpha x's let you do? Let's say someone hands you in the fan a random vector in the fan. Here's a random vector, right? How do you know which Feynman diagram cone it's in? These are all equivalent things to what we talked about before. Well, naively, you'd have to look around. Is it in this cone, that cone, that cone? You have to scan over all roughly 4 to the n cones until you find the one that it's in. If you have these alphas, what do? you have order n squared x's, right? So polynomial number. You just evaluate the alphas on t. All of them will equal 0, except n minus 3 of them, which are the cone that it belongs to. Okay? It's really doing something, right? It's sort of, without thinking about the diagrams, it's telling you what the diagrams are. Right? And as you move around the space, it tells you exactly which diagram you're in. But what's remarkable is that it's doing it, well, this is the claim, and what's remarkable is that it's doing it without caring about anything other than one curve at a time. Okay? So let's see. Let's see how it works. Let's just do it with two examples, the two examples that we just talked about. Oh, sorry, one that we talked about. So let me do a simpler one. Let's do, okay, so this was U trop for who? Who did I do there? This was 1, 4, right? Let's do U trop. So U13 was Y13 over 1 plus Y13. So this is e to the minus T13 over 1 plus e to the minus T13. And so U trop of 1,3 is negative T13, negative max of 0 and minus T13. All right, so let's just look at these two examples, and just so you see how it works. So what is alpha 1,3? This is supposed to be U13 trop. So alpha 1,3 is negative T13, negative max of 0 and minus T13. Okay? So what is this function? Clearly it's piecewise linear, again, right? So this didn't know anything about these cones or anything, right? So in particular, it's going to be piecewise linear on these cones. That's also, of course, going to come out. But let's see what this guy is. So what is alpha 1,3 here? Well, this is very easy, because T13 is positive here. So max of 0 and negative T13 is 0. So in here, it's negative T13. Okay, also T13 is positive here. So in here, it's negative T13. What is it? Anywhere where T13 is negative, then negative T13 will be the max. And now I get negative T13, negative T13, which is 0. So on this side, it's just 0. Okay, and that's exactly what we saw it had to be before. All right, so let's look at alpha 1,4 is a little bit more juicy. So alpha 1,4, there's the expression for it. Let's see what this looks like. Whoa. So in here, what do we have? In here, T13 is positive, T14 is positive. So in here, we get negative T14 plus 0 minus 0. Okay? So in here, it is negative T14. What is it in here? And here, T13 is positive. T14 is negative. Right? So that's negative T14. T13 is positive, so this is 0, but T14 is negative, so the max of all of these things is negative T14. Right? So it cancels, so I get 0 here. Anyway, you can work it out that it's 0 there, 0 there. And what is it in here? This is a little more interesting, because here T14 is positive, but T13 is negative, but T13 is not too negative, right? Negative T1, so T14 plus T13 is still positive, right? T14 is bigger than T13. So what do I get in here? I get negative T14. In here, because T13 is negative, I get negative T13, okay? But in here, I get, oh yeah, and that's correct, and this is 0. So I get negative T13, negative T14 here. Okay? And that's right. So this is something, this guy is piecewise linear, so it's equal to minus 1 here. It's equal to 0 here. It's equal to 0 here, because it's T13 plus T14, and it's 0 consistently everywhere else. Okay? All right. So that's the zeroth order claim. All right, is that these alphas that give us global Schwinger parameters are actually the tropicalizations of these simple objects that are associated, these U variables that are associated with any, the U variables that are associated with any word. All right, so for example, you can now just work out what you see, the words are, let's say you're at tree level. You're allowed to choose any old triangulation you want, right? So there's a very simple triangulation that just looks like kind of a comb for any n. That kind of diagram. And here it's extremely easy to work out what all these u's are. Basically, every polynomial that you ever see looks like 1 plus yi plus yi plus 1 plus dot 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 plus yi plus 1 up to some yj. Everything looks like that. Okay, everything looks extremely simple. You can work out all the u variables. And so you can write down a global Schwinger formula for the tree amplitude. Right? So let me just write it down here. But now it's an integral over a single object. Okay? So the n-point tree amplitude is an n minus 3-dimensional integral, t, e to the sum, and let me actually write what it ends up looking, right? So e to some minus s. And when you write everything back in terms of e, I'll just even write everything back out in terms of momenta, where the s is equal to, this just to show you there's a concrete formula here. I equals 2 to n minus 2. J equals I plus 2 to n. 2 pi minus 1 dot pj minus 1. We could write all these things in terms of x's, but I'm just writing it this way just to show it in the end in terms of everything. And then I have a sum from j equals 3 to n minus 1 of just the tj's, x1j plus m squared, if I have some mass squared. Okay, so that's just what comes out of shuffling the exponents, where xij are our usual pi plus dot dot pj minus 1 squared. That's as we defined before. And these fij are some combination of the alphas, which just turn out to be the max of 0, tj plus tj minus 1 up to tj plus tj minus 1 plus ti. And that's it. Right? So it's a single object, right? Single object, a single exponent. And this is just writing out the exponent. This is just writing out what the sum of alpha xij ends up being. Okay, it's so easy to work out what these alphas are. Here's the one place where the tropical expression makes sense. All these maxes, okay, that's the remnant of the fact that there's this tropical business there. All right. Now, you'll notice that this expression is completely homogeneous in the t's. Everything is linear in the t. That's what you're used to when you have Schwinger parameterization. So you can do the integral over the overall scale if you want, and be left with a one lower dimensional integral. That's what we normally do. Normally in Feynman parameterization, you have the delta of 1 minus the sum of the x's. Okay, that's just doing the integral over the overall scale. In this case, I could do the overall integral over the overall scale if I wanted. And for instance, because it's the integral over the whole space, I can do polar coordinates. I can integrate it just so it's the leftover integral is over an n minus 4 sphere. and then I put this 1 over s to a power downstairs instead of having it in the exponential. Okay? So you can just do one integral over the overall scale and be left with an integral over an n-4 sphere instead of over the n-3 dimensional space. I prefer to leave it this way for now just to make it manifest that it's coming from Schwinger parameterization. To repeat, what's amazing about this formula is that there's no Feynman diagrams. We're not enumerating. We have one object, one n-3 dimensional space. We have some functions that depend on n squared variables, right? In fact, they have at most n terms in them. But this S is piecewise linear, right? That object is piecewise linear, and if I ask for the domain of linearity, like where is it linear, you'd find that this S breaks up into order 4 to the n cones, where it's linear in each one, right? So I put in a polynomial amount of information in, I get an exponential amount of information out. Okay? It sort of divides up the space by itself into the different regions that correspond to the different Feynman diagrams without asking to do it. All right. All right. I want to make 2 more comments, and then we can stop and ask and have questions. First, this was all at tree level. But you can do all of this at loop level as well. The U's are exactly the same. And what's interesting, so the U's are always, the alphas are always, so the alpha for any curve is always the tropicalization of U. But it means that what we're doing is we have, and I'm going to have to be a little schematic here, but we have this integral over our T space, e to the sum over alpha x, x. But some of these x's will have loop variables in them. So some of them will be like L plus P squared and so on. And if we have multiple loops, I have many L plus P squareds. Right? So that's great. That's what Schwinger parameterization is normally for when we have loop integrals. Right? So that means that in this form, I can do the loop integrals once and for all. Doing the loop integrals is a Gaussian integral, like you normally do when you introduce Schwinger parameters. Now, if you're used to doing this for anything other than the most simple graphs, where you can just do the Gaussian integral by hand and you don't think about it, normally in this story, there are things that are known as semantic polynomials that are associated with graphs. Okay? How many of you guys have heard of semantic polynomials? Okay, some of you have heard of semantic polynomials. Well, the idea is that if you have any old graph and you Schwinger parameterize this graph however you want, then, actually normally people don't do it with, they do it with 1 pi graphs like this, okay? Then after you do the loop integrals, you're just left with an integral over the Schwinger parameters. So if the graph has e edges, you have an e-dimensional integral over Schwinger parameters. You've done the loop integration, you've done the Gaussian loop integration, and after you do the Gaussian loop integration, you're left with 2 polynomials that are known as the semantic U polynomial and the semantic F polynomial. Okay? But roughly speaking, this is coming from, when you have the Gaussian integral dx e to the minus ax squared plus bx, this is root pi over a, or the part that comes from the determinant, e to the b squared over 4a. The root pi over a is this semantic polynomial, and the e to the b squared over a is that one. Okay, so that's what you get after you do the Gaussian integral. This is known as the U semantic polynomial. This is the F semantic polynomial. It's a polynomial associated with a graph, a single graph. All right? Now, what are we doing? We are introducing Schwinger parameters for all the curves on the surface at the same time. So we don't divide things up into graphs. We do one giant Gaussian integral, right? And so what we're going to be left with is exactly the same expression, except instead of normal semantic U and F polynomials, they're what we call surface semantic U and F polynomials. They're the analog of what you get for a single graph, except for the entire surface at once. And I don't have time to explain it, but normal semantic polynomials have a very nice combinatorial description, graphical description in terms of cutting the graph either into a tree or into two trees. And the surface semantic polynomials have exactly the same description in terms of cutting the surface to a disk or two disks. Okay, but instead of talking about it one graph at a time, it's something that's tailored to the entire surface. But the bottom line is that after you're done, you have an integral. At loop level, you've done all of the loop integrations, and you're just left with an integral over this space. So now this is the formula for the amplitude, post-loop integration. It's an integral over the same space, but now we're going to have u of alpha, but this is the surface u, to the d over 2. Sorry, I forgot to say it. Yeah, that's the number of space-time dimensions d over 2. E to the minus the surface f over the surface u. So in here, the f contains all the information about the external kinematic data, okay? But this f and this u depend on all the Schwinger parameters for all the curves on the surface, not just the ones for a particular graph. And the polynomials are polynomials, formal polynomials in all those variables, except in this expression, the alphas are substituted by alpha of t in the way that I just told you. So they're the global Schwinger alphas. These alphas are alphas of t. So all these alphas in here are these alpha x of t, which are exactly the ux trop of t. Okay, so I'm not expecting you to understand this in any detail, but other than just to get an idea that this is really global Schwinger parameterization, which at loop level means you can do the loop integral. You can do the loop integral, and now you're left with just an integral over this t space of something which, as you move around in t space, you're going to get the Schwinger parameterization for this diagram and that diagram and that diagram, but you don't have to think about all the diagrams. It's all combined together for you. Okay? The magic is that it's possible to describe these u's efficiently without thinking about the diagrams one at a time. Okay? All right. Okay, and a final comment. I told you a few times that we have this problem, that we have this infinity. Once we go beyond, once we start seeing the annulus, we have this infinity. The infinity means that we're double counting or maybe infinitely counting the same diagram over and over again. That means that this object has a symmetry in t space. It's a symmetry that would do a piecewise linear transformation that would correspond to going from one triangulation to another, doing this twist that we talked about. So that's this action of the mapping class group, and that's a spurious infinity that you have this integral over t. To get rid of this spurious infinity, you have to mod out by the mapping class group here. Okay? Now, this is something that we haven't said anything about a worldsheet, nothing. This has nothing to do with string theory. This is all about particles, right? But I said already at least some of the fancy words. What we're talking about before was Teichmuller space. This is what turns into moduli space. All right? And this is kind of a well-known, not totally trivial thing to do, to come up with coordinates on moduli space. And normally, some way that you think about it is how do you find a sort of a fundamental domain, a kind of fundamental region in T that then, under all the copies, sort of tiles the entire space, and that's difficult. That takes some cleverness. But there's another way of doing things that takes inspiration from some ideas of Mirzakhani that explicitly told us how to do these things without finding a fundamental domain. And I won't explain this in detail, but just so you have an idea, the idea is really a variant of the usual Fedorov-Popov idea that we applied to a gauge theory, except adapted to this setup. And there's just a simple kernel here, K, which depends on these alphas. Okay? So there's a simple way of choosing a kernel K that does the modding for you without identifying a fundamental domain. You don't have to sort of by hand identify fundamental domain. You just insert some factor in here, and then you're done. This factor also has the pleasing property that you don't have to compute all the alphas for all the curves on the surface, because this factor vanishes over most of the space. It's only non-zero for some small region of the space where some small number of the curves turn on. So you only need to compute some small number of the curves to shove in there to get the answer. Okay? And then we're really done. Once you figure out what that kernel is, we're really done. This is not a formal object. It's a numerical integral. You can put it in Mathematica, do and integrate, and get the answer. Okay? So it's not formal. It's really an honest integral over a single object that's supposed to give you the whole amplitude. Maybe I can show you what it looks like at one loop. Okay. See, it'll look very similar to a tree level, but if you're familiar with what Schwinger parameterization looks like at one loop, you'll sort of recognize it in that way as well. So at one loop, so A for all the amplitudes at one loop is now an n-dimensional integral, not e to the minus s, but now it's going to have an over. This really is f. Let me not. I don't know what I should call this. E to the minus something. I'll even write it there. But it's over the sum of all alpha I to the d over 2. Okay, and this is x of minus the sum of alpha I, alpha j, xij, that's it. Where alpha I, so alpha I, with this definition of f, is just fi I plus n. Okay, so just where you cycle all the way around, right? So you'll recognize, those of you who know about Schwinger parameterization, you'll recognize the f polynomial has these quadratic pieces in it, right? So that's the quadratic piece. This is the u polynomial for like a box diagram, has a sum over the alphas in it. But what's interesting about this is that it's a combination of tree and loop, right? So this is not just a given box diagram. It's the entire amplitude. The entire amplitude has pieces with tree propagators, loops in it, right? It's summing all of them together into a single object. That single object, okay? And you can put that single object on a computer and integrate, and you get the answer. Okay? Oh, well, all of that is the usual story, okay? So we could go to, sufficiently low dimensions. There's a whole very interesting story about how you think about ultraviolet divergences in this picture and so on. There's actually, there's two more terms here, just for completeness, but it's somehow related to your question. So there's the sum over I, I'll call it T, fi I plus n. I guess I could call that alpha. Oh, sorry. Alpha I is this fi I plus n minus fi I plus n plus 1. It doesn't matter. I'm just so you see there's a concrete formula plus b fi plus 1 I plus n. Okay, so what are these terms? T is a universal variable that I'm associating with all the tadpoles. So that propagator you might call 1 over 0, right? But it could also be 1 over little m squared, right? So all of these propagators I'm calling 1 over t, And similarly, you can have bubbles on the external legs. If you have these bubbles on the external legs, this might also be 1 over 0, but I'm going to call this guy 1 over b. Right? And in this way of putting everything that we have in even the usual renormalizations here. We renormalize the tadpoles and we renormalize the bubbles. Okay? And so those variables t and b occur in this expression. All right, so yes, absolutely. You have to think about the ultraviolet there, but all of that is now just the standard story. You can go to low enough dimensions where it's convergent, analytically continue, directly think about where the divergences come from, and there's a whole interesting story about how the singularities and the divergences are captured in this tropical way of thinking. Okay, but from this, I hope you get the idea of what global Schwinger parameterization means and how we can think about the full amplitude as the integral over a single object. Let me say in my last 5 minutes, one last thing. So we define these U's, and the U's are these juicy nonlinear things, and then we've kind of taken a piece of their nonlinearity. We've looked at the leading way they behave as you go to the sort of boundaries of the space, okay? And we have used that to give us this picture of global Schwinger parameterization. But you might wonder if these U's nonlinearly mean anything, okay? And this is an exercise that you can do just with the U's that I defined at 5 points. I unfortunately erased them, okay? But you can notice that the U's satisfy the following remarkable equation. I'll tell you what the equation is for any surface, okay? If you take the U variable for a curve x, plus the product over all the other curves on the surface, uy, to the exponent given by the number of times the curve y intersects the curve x, this adds up to 1. Okay? So this is a really remarkable formula. So what does this mean in the case of the disk that we just talked about? For example, at 5 points. At 5 points, it's a very simple formula. 1, 2, 3, 4, 5. This tells me that if I look at U13, and now I have to take the product over all the other curves, which are 1, 4, 2, 4, 2, 5, 3, 5, right? But to the number of times they intersect 1, 3. So 1, 4 does not intersect it, so it doesn't appear. 3, 5 doesn't intersect it, so it doesn't appear. But 2, 4 and 2, 5 intersect it. So it's U24, U13 plus U24, U25 equals 1. Okay? So you can write these equations, and you can check that the U's that I defined satisfies these equations. Right? Now, these are remarkable equations, because these equations tell you something. If you ask the U's to be positive, first of all, these equations automatically tell you the U's are less than 1 as well. Right? Because the sum of two positive things adds up to 1, so the U's must be between 0 and 1. A. But B, these equations tell you something amazing, that if some U sub x goes to 0, well, the product over all the other y's that intersect it has got to equal 1, but all the y u's are between 0 and 1, so that's only possible if all the other u's go to 1. Okay? So all of the u's that intersect x go to 1. Right? So this is, I mentioned before, just as an observation, you could have observed that as you go to infinity, some u's go to 0, the other ones go to 1. But it's a consequence of a much more rigid fact. Okay? This equation is not just about the asymptotics. This is an exact statement that's sort of true everywhere. In fact, I could have begun this entire story, but it would have seemed a little even more out of the blue, perhaps. But if I wanted to tell someone to reconstruct everything of these lectures that I told you today, from one key formula, they're on a desert island, I would give them that formula. Okay? You look at a surface and you declare that you're looking for solutions to this equation. U of x plus the product over all y, uy to the nyx equals 1. You see, it's not obvious that this has interesting solutions at all. Naively, you have as many equations as you have unknowns. So if anything, it should have solutions in points, maybe. Like even at 5 points. I have 5 equations and 5 unknowns. but they're dependent on each other in a non-obvious way, so that, in fact, it has a two-dimensional space of solutions. Okay, and that two-dimensional space of solutions, one way of parameterizing that two-dimensional space of solutions is in terms of the formulas I gave you for the u's in terms of the counting problem. There turns out to be another way of parameterizing solutions of these equations involving notions of hyperbolic geometry. It's a second way I've said already a few times. These u's are expressed as cross ratios of points in hyperbolic space. And the second way is a little bit more closely related to things that are seen on the world sheet, at least at low loop order, partially because this is a way of thinking about the Teichmuller space and the moduli space that's much more closely connected to hyperbolic geometry, whereas the standard way of doing things in string theory is more closely connected to the complex way of thinking about Riemann surfaces. But in any case, these variables and these equations at tree level were actually first written down by physicists, by, I believe, Kobe and Nielsen, when they first wrote down the Kobe-Nielsen formula in string theory. And the reason it's useful is, now the reason it's useful you'll now understand. Okay, but, okay, so that's one fact. But now let's remember what it is that we're doing. So remember, what we're doing is we wrote down a global Schwinger form that looked like the dnt, right? Even at tree level, e to the sum of alpha x, x. What was alpha x? Alpha x was equal to ux trop. And what was ux trop? Ux trop was u itself as the t goes to infinity, goes like e to the ux trop. By the way, and remember, all the yi were e to the minus ti. So I can write this dnt part, I can equivalently write as the integral of 0 to infinity dyi over yi, right? That's what dt is, when y is e to the minus t. But what about this part, this e to the alpha x? So this is the product, this is the same as the product over all x, e to the alpha x to the x. Right? So e to the alpha x itself is e to the ux trop. Okay, so I could equivalently just write this as e to the ux trop. What is e to the ux trop? E to the ux trop is just ux itself if you go far enough out. So it's natural to ask, what happens if you just don't go far enough out? Just leave it as ux everywhere. Right? So that's what we're going to do. Product over x, ux to the x. Now these are just the full nonlinear x's, no tropicalization, no limits, nothing. Right? What do you think these are? These are string amplitudes. At tree level, these are literally the Kobe-Nielsen amplitudes. And let's just quickly see what it looks like in the simplest case at 4 points. So for n equals 4, we didn't do this example because it was so small. But in this case, our fan is just one-dimensional. So I have 1, 3, and 2, 4. And I can work out my curves, 1, 3, 2, 4, and it will not surprise you that u13 is y13 over 1 plus y13, and u24 is 1 over 1 plus y13. So they're both less than 1. They add up to 1. Okay, that's what the formula is supposed to be in this case. So what are we supposed to instruct it to write down now? Okay. We're instructed to write down the integral dy13 over y13, u13, which is y13 from 0 to infinity, y13 over y13 to the x13, u14 is 1 over y13 to the x24. Okay, so this is integral 0 to infinity dy13 over y13 y13 to the x13, 1 plus y13 to the negative x13 plus x24. And this is the Euler beta function. This is gamma of x13, gamma of x24 over gamma x13 plus x24. Okay? So that's the Veneziano amplitude. Of course, as x13 and x24 are much smaller than 1, this reduces to x13 plus x24 over x13, x24, which is exactly our usual friend, 1 over x13 plus 1 over x24. So if we work with the full nonlinear U's, we're getting string amplitudes. And why do we know ahead of time these things deserve to be called amplitudes? Because they have the magical factorization property built into them. Okay? Why do these things factorize? This way of writing it makes it obvious that they factorize. Where do the singularities of this integral come from? They use, you see, this dy over y has a logarithmic divergence as y goes to 0 to infinity. So if I go to the boundaries of my space, this has a chance to develop a divergence. It's the u's, the boundaries are a certain u goes to 0. And if the power is positive, it's going to regulate the divergence. Instead of getting a divergence, I'll get 1 over x. All right? But that means that if a certain x goes to 0, I'm going to get a divergence from the region where that u is going to 0, because it's no longer being regulated, right? So if I send some x to 0, I'm going to get a divergence from where that u goes to 0. This is where this magical binary property comes in, okay? Because when a given u goes to 0, all the incompatible ones go to 1. That means the ones that go to 1 drop out of this formula. And all I'm left with are the integral over the u's that are compatible with the one that I sent to 0. But then that's just exactly the same formula with the ones on the left and the ones on the right. Okay? And that's why this object factorizes even, you know, at finite alpha prime, if you like. So I didn't put it in, but if I put an alpha prime here, then what we're doing is imagining that alpha prime is finite. If I send alpha prime to 0, then I'm localizing the integral on the places where the x's, where the t's go to infinity, and that reduces me back to the field theory limit. But even at finite alpha prime, this thing factorizes into the product of lower amplitudes as any x goes to 0. Because now of this interesting binary property. This is now something beyond just the fan. It reflects a fact about the nonlinear structure of the U's themselves. And this also ports to higher loop order. But then there's more of an interesting story. Because when you go to higher loop order, you get to decide something. You get to decide, in writing this formula down, do you want to keep all the curves? Or starting even at one loop, you have the possibility to include curves that self-intersect themselves. Okay, if you include curves that self-intersect themselves, in this U formula, the same U will occur in both terms. So that means that U can never go to 0, because it occurs in both terms. So that's why the variables that self-intersect are never relevant in the field theory limit. You can keep them or not, depending on your taste. Okay? If you throw them out in the field theory limit, you'll get the amplitude. You keep them, you'll get the same amplitude. It doesn't make any difference. But it turns out that if you keep them, you keep all the curves, which is, in a sense, the most natural thing to do. Then, even at one loop, you have a big infinite product over curves that includes self-intersections. Self-intersection 1, 2, 3, any number of self-intersections. That means that these integrals that already were sort of fairly simple rational functions, beginning at one loop, they're going to have an infinite products in them. And those infinite products exactly give you the Jacobi theta functions that you're used to seeing in the standard way of thinking about loop integrals in string theory. But of course, this picture ports to any loop order. You're doing the same thing all the time. It's the same formula all the time. Okay? And you can check at low loop order up to the annulus that if you do include all the self-intersecting curves, you really do match what you get with the usual bosonic string. But you have the choice not to. If you don't, you have a simpler object. And you can do other things with this object. You can take the field theory limit. You can forget about the alpha prime altogether. Just do everything as I told you from the start in the tropical limit. And then you're just doing the fact that all the diagrams are unified into a single object, and all the rest of it is just something that has nothing to do with finite alpha prime to begin with. So the final comment is that with all of this stuff, going back to the picture that we have an expression that's integrated over T space, and the sort of magic is that there is an action, the sum of alpha x times x, that's piecewise linear, and that sort of generates all the diagrams everywhere. Now you can ask, can you do this for a general Lagrangian? A general Lagrangian is now going to have interaction vertices. So what you want is some analog of this picture where not just the denominators, but the numerators are captured by piecewise linear functions that turn into the numerator that you want to associate with every Feynman diagram in the different cones. And that turns out to be possible. And there's essentially a one-to-one way. You give me any Lagrangian for these colored scalar fields, or any number of them, or for that matter, you can give them vector indices. You can do it Yang-Mills. But really, beginning from the Lagrangian, you can take any interaction vertex in the Lagrangian and translate it to a tropical function, to a tropical function that you add to the fan, which has the property that as you're moving around the space, it morphs, and in every cone, it turns into the numerator that you expect for that diagram. Okay? So that's one direction that you can go. But the more interesting thing, which I alluded to in the very first lecture, is that just this simple trace phi cube theory by itself actually contains within it interesting physical theories if you just interpret them properly. Interpreting them properly means that here we've thought about the x's as kinematic variables just for the scalars. But if you expand not around x equals 0, but around non-zero values of the x's, and think about the perturbations around the non-zero values of x's as giving you the kinematics for massless particle scattering, you get either Yang-Mills theory or the nonlinear sigma model. Okay, and the Yang-Mills theory and the nonlinear sigma model are actually related to each other, and they're all sort of continuously related to the trace phi cube theory. So there's sort of one master object, which is this trace phi cube theory, and depending on where you expand it, you can either get the nonlinear sigma model out of it or Yang-Mills theory out of it, all in this same basic rubric. Okay, so that's the thing that I'll describe next week, but I hope from the lectures today, if you're interested in the subject, that you'll have learned enough to be able to think about the subject and hopefully help us push it forward more. Thank you very much.
Any real quick questions, or can we end this section
Well,
for here?
we can ask a few. I think, yeah, it's my flight. Yeah, it's fine. Yes, go ahead. Yeah. Yes, you can do, for example, Yukawa theory in this way. We don't yet know how to do the Yang-Mills story, including fermions. I haven't told you the Yang-Mills story yet, but the Yang-Mills story involves a way of thinking about Yang-Mills in a sort of scalary way. We don't yet know. So we don't know how to do fermions in general, but for example, Yukawa theory you can do in this kind of language.
No?
Yes?
How doable are the integrations when you go to, for example, high loop order?
Well, I mean, they're exactly, it depends what you want to do. If you just literally want to get numbers out of it, it's just Monte Carlo. You just integrate. You get an answer. They're totally not formal integrals. However, what they look like, sort of cone by cone, is exactly the Schwinger representation, the semantic polynomial representation for every given diagram. Okay, so the most minimal thing you'd say is if you just took this expression, you stared at it and say the first thing I want. Let's say someone just handed this to you ab initio to begin with. You'd say, great, I want to understand this. So first, I'm going to look at what are all the places that this guy is piecewise linear, right? Then you do the work and you're like, holy crap, there's exponentially many places this is piecewise linear. Examining that question basically reconstructs all the Feynman diagrams for you, all right? And then you'd say, oh, and so this is the Stringer representation, this diagram, that diagram, that diagram, that. So at zeroth order, we've sort of packaged all those things up into a single object. Where there's room for something interesting to happen is if you expect in interesting theories, and we expect in things like Yang-Mills theory, that the diagrams talk to each other, right? They're not random independent things, that they talk to each other in some way, and that's where this more unified representation should offer some insights that you would not get when you thought diagram by diagram. And if I advertise one limit, which we were talking about with some people before, where definitely something interesting should happen, it's the large n limit, where n is a number of particles. Okay, as the number of particles goes to infinity, we have infinite exponentially many diagrams. We still have a single object, and maybe this is a little bit more obvious from the picture from yesterday. But remember the picture from yesterday, we already had a sort of simple continuum limit in mind, where we just had the wave equation, and then we're just discretizing it. So it's clear the sort of continuum limit can't be so bad. It's just going to turn into the continuum wave equation, right? That's also true here. If you look at these piecewise linear expressions, they simplify. They have a sort of continuum descriptions at large n. And formally, the infinite n limit turns into a certain kind of one-dimensional path integral. It's an amusing one-dimensional path integral with a non-Gaussian measure, okay? But it's an interesting sort of semi-classical problem at infinite little n, which is not an expansion that we normally talk about, okay? But there is a possibility here that there is an expansion at infinite little n, number of particles, what's captured by this unified description. And that's something where I think something really new and interesting should happen. Already at tree level, just to give you an idea, if all the x's are equal to 1, that's already a limit. If you're very dumb, all the x's are equal to 1. Okay, what am I doing? I'm counting the diagrams, right? And if you didn't know how to count the diagrams using nice recursion relation, you didn't know about Catalan numbers, you would have to do some work, and then you discover at large n, it goes like 4 to the n. So that tells you if you take the log of the amplitude at large n, it goes like n times something. That's a classic large n weak coupling thing, that the object goes like e to the n times something. So the amplitude is going like 4 to the n times something. Okay, and that something is just a constant in this case, but now if the x's have some variation, you would expect it to have some dependence on what that variation is, and there should be a theory that captures what the amplitude is and how it depends on the x's. That's someplace where I expect this way of thinking should actually offer something new. But before that, at least if you just want to numerically get the integrals, you just shove it on the computer, do and integrate, and yeah, so this is sort of sidestepping the job of enumerating the diagrams, string parameterizing each one, adding them up. Just one expression that you can write down is doing all of that to begin with.
Well, unfortunately, Nima has to go, so let's thank him again for the
Thank you.
great series of lectures.